Hello, after the series of tutorials with this simulator, the WWER nuclear simulator, I found a second simulator very interesting thanks to the Comrade 3DR in YouTube. He has two videos, very good videos. I advise you to watch them. One is a tutorial and the other one is an exercise using this simulator in which he performs a warm startup of the reactor. So let's see, we have all these tasks in this simulator and today we'll try to do one of them. WWER-1000, it's a Russian design from the year 75. I think it's the third iteration or so. There are two previews, less powerful, to this 1000. 1000 stands for approximately the electrical power output, so 1 gigawatt, this is 1000 megawatt, and you guessed it, yes, WW stands for water to water. It's a water-cooled, water-moderated energy reactor. BW stands for boiling water, so very different designs. Here we don't have boiling water in the reactor is pressurized and we have boilers in the primary circuit, and the turbine is in a secondary circuit, not in the primary circuit. Very different design and very similar to the also very famous Westinghouse design, very used in the West. So let's see what we can do. If you look at the channel of the Comrade 3DR, probably I think he's doing this task C05, so hot shutdown and start with failures, without failures, middle of cycle. So the middle of cycle is the state of the fuel. We will do maybe this. Yeah, C01, hot shutdown and start up without failures at beginning of cycle. So here the fuel is much more enriched, so it's more reactive, and probably we have less neutron poisoning. So the difference between this and this is that the boron or boric acid concentration is much higher here, because we're at the beginning, so we need to compensate for the reactivity of the fuel, and there is much more boric acid. So let's start it. What's this error? I don't know. Yes. Okay, we have the main control panel here. I advise you to follow the tutorial of our Comrade 3DR. I will not go through all the functions because he already explains it very well. So what I want to do here is to take advantage of this high boron concentration, 7.5, which is the one used at the beginning of the fuel cycle, and we'll reduce it a lot to increase reactivity and bring this up to speed much faster after the hot shutdown. So let's start the simulation. Okay, everything is fine, and scram, everything goes down, and the first thing I will do is to use this interface here. This is a trick I'm using actually, because in reality you will not have this here. But you have here the core model, which is the core of the reactor, which interacts with the thermohydraulic 1C model, which is this, the primary, and also interacts in the other side with the boron exchange 1C model. So this is chemistry mostly. And I will select this boron and select auto, and this will try to compensate for the very low reactivity. And you see how fast the boron concentration is going down, 7.40, and so we'll just take advantage of this simulator feature to get a very low boron concentration in the water, and then we'll increase activity much faster just withdrawing rods. Okay, now let's go through the tab. We see a lot of blinking. Pressure in the primary less than 140. Yeah, we have all these problems in the steam generators. TK disbalance, and the main steam valve closed. Okay, let's release this cram button. Let's see what's going on here. Yeah, very low pressure in the reactor, 139, but the pumps are pumping water in, so it will be restored in a while. We see the pressurizer also with a flashing pressure alert. TK, we had a TK imbalance, if I'm not wrong, so let's open these valves. Open this pump. Let's set it in auto. Add this anti-return, so let's put it to the left. Open. Okay, so this should solve the imbalance problem. And for the moment I will not touch the boron concentration, or I will not add water because I'm using this trick. I'm using this trick here. As you see, we are already at 6.2. So just to have an order of magnitude, at the beginning of cycle we have a boron concentration of 7.5. Middle of cycle we have 3, something like 3 point something. And at the end of the cycle we'll get close to 0. So let's see how low we can get it. Let's see. Okay, for the moment I don't say anything because I have no idea whatsoever. Let's look at the secondary. Okay, we see the turbine. It's shut down. Let's put the MSRV modes in start mode. Everything is fine. Everything is fine. We have the pressure in the primary high on 140 already, so probably you can already start withdrawing rods. It's not selected. Let's select the rod 1. Here, not yet, there is something wrong. Oh yeah, there are many things wrong. Blinking the block, repeat the block, MSV close, yeah. That must be okay, let's try now. Yes. So we can already withdraw rods, but I will not continue, we'll just let this numerical trick to go a bit further. Let's get the boron concentration a bit lower, and then let's see how this helps us to get into power without having to withdraw too many rods. Of course, this is just a trick that I'm doing in the simulator. Don't even think to do this in a real reactor because I have no idea what I'm doing. Okay, you can only do this like if you are operating the plant and like the general secretary of the party in Moscow calls you like, hey, we need to have the reactor in full power in 45 minutes, and then you are screwed because following the normal procedure you will, at least it will take 1 hour. So if something like that happens, oh look, I'm getting to, let's stop it. Oh, I was very close to have a scram. I stopped it right on time. Let's continue a bit more. So less than period of 20 seconds, you get a block of withdrawn of bars, I think, of rods. And period lower than 10 seconds, you get scram. So all the rods are inserted in a very fast way. So we don't want that. So I was saying, don't use this technique, never ever, only if the general secretary of the party calls you from Moscow and tells you are in a hurry, you really need to bring this reactor up to power in very short time. In that case, you are allowed to do this very unsafe procedure, otherwise don't do it. And I think I will stop it. 4.4 is it's a value more likely for medium of cycle rather than beginning of cycle of the fuel. So let's start with drawing rods. Yeah, and stop this numerical trick. So we have this table 4.44, and we will continue increasing the power by withdrawing rods. While I'm withdrawing rods, I cannot point to you other things in the screen because I need to have the mouse in this switch. It would be great if there was something that allows you to leave the switch in the withdraw position and do other things, but maybe in reality you can do with some scotch or some metallic piece attached to it. Let's have a look into the period. We are in 40 seconds, 37 seconds, 35 seconds. Let's be careful when we go below 20. I'm not sure it would cause a block in the withdrawal below 20. Let's see if there is some alarm. For sure at 10 there is a scrum, so 10 is a value not to approach. We're at 14. 14 it's fine, 13 it's fine, 12 it's fine, but now let's be careful. That's great, it increased without releasing the button. 11, okay, let's stop this too close to 10. And we can already see that we're at 0.8% of nominal power, so that's great. In just 8 minutes after hot shutdown, we're already at 1% power. That's really, really great. So it seems I can explode the period until up to 10 or down to 10. So let's do it. Yeah, 14, 15, and the power is 3%. So when we're at 5%, I will go to the turbine to connect it. 17, okay, now it seems the period is getting higher. That's not good, but we'll have to deal with it. Okay, yeah, period going to infinity. Okay, let's see what is all this blinking. Yeah, period below 20. That's totally fine, I know what I'm doing. And that's not good. What happens? A level? Too low level? Pressure a bit low, but getting higher. Yeah, that's fine. So we'll go to connect the turbine. Here, differently from the other simulator, the WWER, we don't need to synchronize by ourselves. This is done here. In this alternate current symbol, someone else is taking care of that. So we just click to the MSIV valves, which are these 4 valves. And here we click auto. And hopefully, yes, it's going up to power. We see the number increasing, and this is the power. Yes, 0.06, it's roughly 6%, which is the power that we are creating here. So that's perfect. The turbine is connected. We can already go into P1, normal working mode, and everything looks fine here. Let's look at this. Decay disbalance, I don't like that. Why there is a disbalance? Anyway, it looks fine. What I will do is to add some distilled water. Open this valve, and turn on this pump. Let's set it in auto. Yeah, and this adding some distilled water that dilutes the mix in the reactor, so the concentration of boric acid decreases. And hopefully this will help us with bringing this up to power. Let's continue withdrawing rods. So we are just with the group 1 and we are at 7%. I cannot believe that. I cannot believe if you not follow the normal procedure, it will take a really long time to reach 8% of nominal power. That's very good. And we are at 9, now 10 minutes of simulation. Why it jumped to 12 suddenly? Is there a bug there? We're at 9:59 and suddenly we're at 12 minutes. I really don't know what's going on. Okay. Period of 100. Very good. Nominal power 10. I like this. It's going very smoothly. This Russian reactor is really good. I like the hexagonal pattern. I really like it. It's like a really slick business-like design. Okay, the second group already at number 2, 28% of the total. And one interesting thing of this rod sequence is that the groups are somehow mechanically interlocked. So when you are rising group 1 and you reach 80%, it will start like dragging the group 2. So when you reach 100% with group 1, the group 2 is already at 20%. I guess this is done to reach more linearity along the withdrawal of rods, because the effect on the increase of power is higher when you are withdrawing the rod at about 50%, so in the middle of the reactor. Why? Because when you withdraw rods, imagine the rod is inserted at the maximum bottom position. When you are withdrawing this rod, you are creating a void in the bottom of the reactor. So this void is likely to allow neutrons traveling from less quantity of fuel than if you are doing the same in the middle of the reactor. So while you are withdrawing like group 1, 2, 3, 4, you will create kind of sinus function in which each time you pass the 50% withdrawal, you will have a faster increase of power. And by interlocking, having this like 20% mechanical overlap, I guess you are getting a more linear increase of power when you are jumping between groups. So I think this is really intelligent, clever Russian design. Very good, I'm liking this. Okay, we're already at 88% of group 2, and if we pay attention to group 3, we see that the group 3 goes to number 1 as we go to number 9 now in group 2, so this is the interlocking I'm talking about. And the nominal power is 32%. Period 80 seconds. Everything goes fine. Maybe when we reach at 50% thermal power, I will have a look into the turbine, but everything looks fine. P1 going to 155.76, very close to the nominal value or design value of 160. P2 is perfect at 60 bar. Yeah, that's very good. We're very close to 50. And we are withdrawing group 3. That's a really success. Okay, I will stop now. 1 second and let's have a look into the turbine. Yeah, that's fine. It's there is some okay. You need to scroll down and up to sometimes to see all the indicators. Pressure in the steam generator 60.9, 60.3 in the main pipeline. That's fine. 60.1 in this pipe going to one of the turbine entries. Yeah. Okay, let's continue with drawing rods. This design, I mentioned it before, the WWER-1000 or VVER in Russian. It's from the year 75, and this was really a design that was not relying in very precise numerical simulations to optimize all the dimensions and parameters, but mostly they just over-dimensioned or over-designed most of the things. So if they were not sure if using 3.3 or 3.5 millimeter of thickness in some pipes, and they needed a very heavy finite element simulation to decide between 3.3 and 3.5, they just use 5. Who cares? Just put more steel. Who cares? Don't lose time with numerical simulations. This must be a workhorse. Very reliable, and material is cheap. So just do it cheap and reliable. And it's really reliable, and it's a very nice design, I would say. The fact that it allows you to go down to period 10 seconds, it really tells a lot about the design. If it was not sturdily made, they will put you a limit at 30 seconds, but this is really, really reliable and safe. And later on, like the 80s and 90s, Soviet Union and later Russia started to switch, or let's say abandon, the RBMK-1000 designs in favor of this water-to-water pressurized reactor design. The RBMK is mostly a military design. We are getting close to 100% of nominal power. I will stop drawing rods. That's nice. Yeah, we're at 95. I will just wait 1 second for this to stabilize, and I will continue later. So as I was saying, the RBMK-1000 is mostly a military design. It's not a water-cooled, it's something like graphite moderated CO2 cooled. I'm not sure now. I'm not sure, sorry. But it's mostly designed made to produce plutonium and to be operated and refueled without stopping the operation. So you can continue running the operator while you change the rods to add new fuel. And these pressure water reactors are totally different. Even if you can operate them to produce plutonium, usually they are not, because when you operate at 100% of power, you don't produce that much plutonium. So this is mostly a design for civil uses, for electricity generation. Okay, let's continue. Carefully, because we're very close. 98. We have the EP set point 207, so it's fine if we go past a bit, but let's not create a scrum now, it would be a pity. Yes, 100. Yes, a bit more. I want 100. Okay, 100.2, that's fine. And I connected the ACP, so that's automatic rod control. So it will just keep this power, and it will do whatever is needed with this rod group to keep it at 100.2. But I don't like 100.2. Okay, now it's at 100.5, 6, 7, 6, 5, 4, 3, 2, 4, 3. Let's click when it's 100. Come on, go down a bit. No. 2. Okay, I will connect the automatic control at 100.2. That's totally fine. There is an imbalance in the decay. It seems temperature here. Well, I don't know why. I will stop this. Close. I don't want to alter the boron concentration now. I will leave this open. Okay, that's fine. we still have pressure, not fine. Okay, it's too low, but increasing. And here it's everything fine. Okay. Let's see the turbine. Turbine is fine at 93% of rated power. P1. Bypass set at automatic. The pressure is increasing, so it will reach the nominal value of 160 at some point. And we have the automatic set correctly. We have 100.2 here. We have the period to infinity, boron concentration 4.4. Why is it moving? Why is it moving? It should not move. Okay, it's fine now. 2.4. I don't know why it was moving. And we have the reactivity close to 0 as it should be in nominal. Okay, so I think this will be the end of this video. So you saw how to bring up to power after a hot shutdown a Russian reactor WWER-1000. Not sure this procedure is legal. I'm not sure about the downside of doing so. Probably there is some downside. And you see, to do this we only needed to move 4 rod groups, and the fourth is just at 50%, and it's running at 100.2. So okay, I hope you enjoyed this video. I will stop the simulation here. We did this in 23 minutes. Probably we reached 100 in 19 minutes or so, or 20 at most. So we use 1/3 of the hour usually needed to bring this up to 100% power in these conditions. Okay, I hope you enjoy it. See you in the next video. Bye.